Hello and welcome back to the Law of Exception channel for this second video. By the end of this video, you will 100% understand why prime numbers can only be divided by themselves and 1. You'll understand it, like, for sure, really. You'll also understand why pi, the famous irrational number, is endless and never repeats, even though, as scientists know, we know it's not completely random. And you'll know why. And last but not least, I'll show you why the standard numbering system that we have, 1, 2, 3, 4, 5, 6, etc., has this strange distinction in even and odd numbers, because all three are explainable through the law of exception. Now, of course, a video like this is best enjoyed with coffee, and some of my former viewers from my other channel were reminding me, so of course, have a nice cup of coffee with this video and enjoy. Let's dive in. My name is Florian Roos. Please like and subscribe, as this is a new channel, so very important. Now, in the previous video, I explained for the first time about the law of exception. Now, if you haven't seen that video, I highly recommend watching that after this video, because the law of exception is a really, truly exceptional concept, and in that video I go much more in depth as to how I kind of discovered and found that, and some of the bigger nuances as to how to understand it. But simply stated, every single scientific law and principle that we found so far in history is at a maximum of 99.99999% accuracy. So the laws of Newton, when we first discovered them, they were believed to be 100% accurate, to predict how everything moves accurately. But they turned out that they were not. Einstein's laws that came after, for a second there, were really thought to be 100% accurate, but they also turned out not to be. Now, of course, we famously have quantum physics laws, which again are very accurately, but there also we found that they're not actually completely accurate. So they're great, but there are plenty of places where they don't work. And no matter what science has tried, we have never been able to reach 100% certainty, 100% predictability on anything through any scientific system. It just doesn't exist. And so what is the law of exception? Well, in essence, it's the realization that 100% sure, 100% certain is not possible. That is actually a hard truth. Strange, paradoxical, but true. So whatever we do, whatever we make, whatever truth, in quotations, we learn, there must always be an exception. Or in other words, everything that is real must remain temporary somehow. Everything has to be temporary. Nothing can be complete, for sure, certain, for everything. So anything that is not temporary isn't real, can't be real, in fact. And so that's kind of a monumental realization, to take that seriously and apply it to more or less everything. And in the previous video, I demonstrated how this realization, nothing can be certain, proves that zero and infinity, two concepts that are absolutely central to math and science, are actually imaginary concepts. Both of them don't exist in reality, and by essentially removing both concepts, so both zero and infinity, from numbers, we remove them from math altogether. So we take two ideas, two concepts that just don't exist, but that are weaved into everything we do mathematically, and also into our thinking very deeply, because they've been in math so long, and we just remove it, giving us a completely new series of numbers that I call the probability numbers, that are suddenly, because of that, able to describe reality way better, in a way different way than we ever had the possibility to do before. So that's kind of the short version of the first video. Now in this video, I'm going to show you, I think actually for the first time ever, what it really means that our world, our reality, is non-random. So that word, non-random, is going to hopefully through this video take on a completely different meaning for you. If you think of a friend that you haven't talked to for years, and then the next day he calls you, right? Now, every single person on the planet has had an experience like that, right? You think of somebody, the next day they call you, or something like that. You were thinking about, a particular car, or like whatever it happens to be, boom, somehow it shows up in your life, right? As you were thinking about it. And I will be the first to agree with you that, coincidence sometimes happens, right? We all see it as like, yeah, this sometimes happens. We've all had that experience, but we kind of a little bit devalue it because that's kind of our culture now. And we say, oh yeah, it happens, but it's not so significant. Well, what if I can show you today in this video 3 examples, one after another, happening right in front of your eyes that prove that there is no coincidence, that the law of exception really specifically means that our world, our reality, our human experience is non-random in nature, down to the very bones. There is no randomness, because I have found by experimenting with the law of exception, for more than a year now, that it's almost like there isn't a good word to describe it, but it almost creates a form of magic. What can almost only be described as magic, the magic of you think of somebody and the next day they call you. The fact that there is a relationship between everything. So hopefully by the end of this video, through the example of the primes, pi, etc., you will get a completely new appreciation, but a truly scientific one, that if you think of somebody and they call you a day later, it's not coincidence. It's non-randomness at work. And it works a kind of a specific way. So let's start with pi, because I think that pi, the number better known as 3.1415, etc., etc., is perhaps the best way to kind of show it. So it's a number that communicates actually a relationship, a geometric relationship, a very central relationship between shapes and forms, we could say. Probably the most famous way to calculate pi, to see this number, is to take any circle and take the diameter of that circle and then divide the circumference of the circle by that diameter, and then you get the number 3.1415, etc., etc. Now, this number is called an irrational number, meaning kind of an unexplainable number, because its decimal, so the decimal range of it, the numbers behind the dot, is endless. Like, it's proven that it's endless. It never repeats. It's an infinite number. But I just told you that infinity is impossible in our reality. So pi is quite literally doing something impossible. And that is why pi is famous, why it's such a famous irrational number. It just goes on for forever and ever and ever. And this is, I think, I've checked everywhere, is going to be the first time anyone explained why pi has this shape and not some other shape. Because I think I can prove that there's a very clear, specific reason why it's that particular shape, why it shows that particular structure. And it's the law of exception that proved to be the key to understanding why non-randomness is expressing pi, the thing that is pi, in that way. So how did I solve this? Well, it starts with the realization that our world, our reality, is non-random. So nothing at all can be completely unrelated. Things just don't happen out of nowhere. There's always a reason, meaning there's a choice somewhere that someone has made that leads to every outcome. So the law of exception tells us 100% for sure there must be a reason for the shape of pi, for this strange, unexplained behavior of the number pi that it is irrational, that it's endless, and that the structure itself never repeats. Now, we should not underestimate the power of that. Many math people, even very sophisticated ones, assume that there are things in our reality that just kind of happen. There are even people with PhDs that have said things to me like, we have no need to understand the cause of things like prime numbers. Like, why would we care what causes them? They think, well, it's just an arbitrary system, right? And that's because many people, even deeply within the science field, they work with this idea of randomness and infinity. It's actually a real, like official part of quantum physics, for example. Like randomness plays a real role in that. It's a mechanism that they believe exists. And so what that leads to, like if you believe in randomness, you create nonchalance, that which every human has. Like, oh, this doesn't matter. That's not, like the attitude that there are things, that there's anything that doesn't matter, that there's anything that is random, is a form of believing in randomness. And so this is a concept that seeps into way more of our lives than just the math, and that's why it's so important. So it's a form of claiming that this, whatever it is, doesn't matter, and it's false, because non-randomness means every single thing, no matter how small, matters because there is no zero. And so there is no such thing as zero influence, which means nothing just happens. Anything comes from somewhere. Everything has a history, has a relationship to everything else. It has to be that way. That's what the law of exception specifically tells us. So we know 100% for sure that pi has some type of structure that is related to what is causing that structure, because it cannot be any other way. The shape of pi cannot be random. So if we look at pi, we have an endless number that never repeats. That's the shape of it, an endless number that never repeats. If we look at that critically, and we know it matters somehow, the law of exception says that anything that is real must be temporary, right? Pi is an endless number that never repeats. But pi is an attempt to describe the relationship between shapes. In my example, the circumference of a circle and its diameter. And we get an endless number without any repetitive structure. Why would that question, what's the relationship between the circumference of a circle and its diameter, why would that give us an endless number that never repeats? If there must be a relationship between that question and the answer, then it has to be because there is no exact relationship between shapes. Shapes cannot be complete. They cannot be perfect. If two people measure, use a measuring tape to measure the same circle, will they come up with the same answer? Will they both decide it's the same circumference or the same diameter? No. If 10 people measure with a measuring thing the same circle, same thing, they will all choose a slightly different value. Somebody will say, well, it's 10.9, somebody else will say 10.98. So every single one of them will be wrong because everything is always moving. We know at the molecular level, everything is always moving. So no circle is truly stable in its size because everything is temporary. That includes the size of a circle. So the circumference is always changing. The diameter is always changing because both must always remain temporary because they cannot break the law of exception because the law of exception is the only law that's always true. So what is the only way to express the truth of that if we are using standard numbers to ask the question. The only way to do that is with an endless number that never repeats. The only way to tell the truth, which the world must always do, is to give us an endless number that never repeats, which is a way of saying, it's like the signature of time itself, that time is the only thing that never ends and never repeats. So the relationship between a circle and its diameter isn't fixed. There is no exact answer, so it's an endlessly changing number that never repeats. The answer to the question is that time itself forbids that it can be an exact relationship. So pi, for all of history, for as long as it has been known, has been kind of screaming at us, shoving it in our faces that there are no exact finite geometric relationships. They just don't exist. But what does exist is a range of stability. And that is what we actually find when we do the same thing using the probability numbers. In probability math, pi is and can only be a range of stability. So it's like saying the relationship between the circumference of a circle and its diameter is around 3.14. It's probably 3.14, but it's always going to be a little higher, a little lower, depending on who's measuring it, because in the end, it's the person that's measuring it who will choose the value. Values can only be chosen by a consciousness, by an observer, but they are not real. There are no real values. And so that is why in the real world, when we actually use a measuring stick, we never get perfect pi. It's only something that can happen when we do purely theoretical math and we use the calculated circumference, the calculated diameter, and when we use those, we get perfect pi. And math throughout history has been obsessed with this idea of like, wow, we get this endless irrational number, what's happening here? That's the reason why. It's literally impossible. So when you ask an impossible question, the world gives you an impossible answer. It's like, it's the perfect answer, really. So now we know why pi has the shape that it has. And you've seen, for the first time, proof of non-randomness, that the reason why pi expresses that way is directly related to how we formulated the question, right? So what we see tells us something. Now, let's move on to the second problem. The prime numbers, because we're going to see something similar here. So we know that the expression of prime numbers being only divisible by 1 and themselves, or the inverse, being divisible by nothing except for themselves and 1, that we know that behavior cannot be random again, right? In the same way as pi. We know that somehow it's telling us something. It's behaving in this way because of some reason, some cause, some choice that someone made is causing primes to present with this shape in the same way that pi is expressing in its way. Now this is actually super fun. Like take a minute and see, maybe pause the video and see if you can figure it out for yourself. I promise, once you see the answer, you will go, how the hell did we not see this before? So maybe pause the video, think about it for a minute. Why are primes only divisible by themselves and 1? Why? What's the reason? So, primes are only divisible by 1 and themselves. So it's safe to say that there must be something about the number 1 and divisibility. It's 100% pointing us in that particular direction. So if we start just by the number 1 and just look at the law of exception again, right? The key to everything, the thing that explains everything. Everything must be temporary. So if we imagine 1 as kind of a perfect circle, a perfect unit, it's not temporary, is it? 1, as meant in the standard math system, in the standard numbered system, is a perfect unit. It's not temporary, it's not individual. Every 1 is assumed to be exactly the same. So if you have 1 chicken and you have another chicken, you can say 1 chicken plus another chicken is 2 chickens. So you're assuming that those 2 chickens are the same thing, right? That's the assumption that's underneath it all, because 1 is the same, you can make groups of 1s, and all the 1s in that group are assumed to be the same, right? That's the whole idea of 1. But the law of exception explicitly forbids that, because it says everything must be an exception. There's only one of everything. Everything is unique because everything is temporary. Nothing can be the same or forever. So that's why everything is unique, right? I explained that in the previous video. That's one of the central proofs of the law of exception, is that everything is exceptional. Everybody's DNA, everybody's eye color, nothing is the same. So by that logic, the number 1 is prime. It defies the law of exception. It doesn't follow the law of exception. So if we take that as a clue, 1 is only divisible by 1 in itself, but it's kind of the central number, it's 1. So let's assume based on this, let's see if we're right. So 1 defies the law of exception by not being temporary. Okay, what about the number 2? So if we take 2 perfect circles, 2 perfect number 1s, well, if you look at the surface of the number, you can divide 2, right? It has 2 parts. So it has the exception, and it has some structure that, 1 can be an exception too. So in that sense, it's sort of unique. It follows the law of exception a little bit. So you could say it's not prime. But at the same time, each individual unit inside of there is still perfect, is still timeless, permanent, forever. So in that sense, it kind of defies the law of exception again. So 2 is actually not prime, and it's also prime. It's kind of both and neither. So it's kind of special. It's the exception, and every system needs an exception. There must always be an exception, and we will see that 2 is actually the needed exception here that kind of proves the rule. So we have 1, definitely prime. 2, exceptional somehow, weird, breaks the rule somehow. What about 3? So if we look at 3 perfect circles. So we have the number 2 here, which we know is kind of sort of maybe follows the law of exception. But then we have 1 perfect unit here again that we can't group with anybody. We can't make even groups because we have this 1 perfect number 1 in here. And so 3 is prime because it has 1 unit that cannot be divided. 1 unit of 1 that cannot be divided. Hey, that matches exactly the behavior. It cannot be divided by anything but itself and 1. The 3 is the first number where we really see that is true. And apparently that's because it has 1 unit in it that is indivisible, that can't be fitted with any of the rest to make an equal, divide. So what if we look at 4? Well, 4, we see for the first time the real structure of all even numbers. Because we have twice 2, so we have 2 separate units, we could say, which both follow the law of exception. They are both divisible, they're both kind of temporal, they have multiple parts, but each individual, okay, still, not divisible, but apparently it's enough. And so this is the structure actually of all even numbers. All even numbers are divisible nicely, right? Then we get to number 5. And immediately we see again, we have here the kind of the structure of the number 4, which adheres to the law of exception. Each part has an exception. But then we add that 1 irreducible unit again that we saw on the number 3. And what happens is, again, it renders the entire number indivisible except by itself, which every number is automatically divisible by itself. And 1, the smallest unit in there, which is indivisible, right? So again, we see only divisible by itself by 1. Why? Because there's 1 indivisible unit in there. What about the number 6? Well, we see the repetition of the number 4. We see kind of 3 units. Each of them is nicely divisible, so again, an even number. 7, same thing. We see a nice even structure, but we get this 1 irreducible perfect unit in there again, and that again causes the entire structure to only be divisible by the entire structure and 1, the smallest part that's in there. The number 8, same thing. We see again clearly the even structure, nicely divisible units everywhere. Number 9, here we get the first non-even, non-prime number, where we see that we had this nice even structure of 8, we add 1, but the structure now get divisible by 3. And so the unit, as they get larger, primes get more rare, you might say, because the more numbers, the more options for divisibility there is. And here we see for the first time that actually all 3 units in there very nicely fit the law of exception, because now we have a unit of 2 and a number of 1 in there, so we have kind of 2 different units really, so it perfectly nicely adheres to the law of exception. Every part of it is exceptional. Now we get to the number 10, we get a nice even number again, 11, and there again we see that on top of this nice even structure we get 1 unit that no matter what you try, you can no longer make even groupings of the entire number, because there's 1 indivisible number in there, 1 indivisible perfect unit in there that just will not budge. And so again, that causes the number to be only divisible by the entire thing and that 1 indivisible unit in there. So it's clear that the clue that we actually got perfectly showed us what the reason is that primes have this structure, that primes show this behavior. So primes are primes because they have 1 irreducible unit inside of them. And because of that, they can only be divided by themselves and that 1 irreducible unit. It's the smallest possible fraction, and it makes every other equal fraction impossible. That is the why. That is the structure of all prime numbers. So our choice to use complete, perfect, timeless, infinite units in our standard numbering system inevitably leads to prime numbers. All this time, the primes have been telling us, showing us with their behavior, that if you choose to use hard boundaries in your basic setup, then you will get hard, strange boundaries inside of your equations, because they will just kind of go from your basic setup into everything else. And so just like pi, once again we see that the power, the magic kind of non-randomness works. The world around us is being truthful. If you have the eyes to see it, if you're aware of the law of exception, then these relationships, however mysterious at first they may appear, they kind of become obvious everywhere. Because once you see that every form of nonchalance, of like, well, this doesn't matter, that doesn't matter, or that detail, whatever, once you see, no, all of those things matters, and you actually make the effort to try to understand why and how it matters, then there's actually super valuable information in everything that sort of goes into our mind. So now we know why pi is an endless number that never repeats, and we know why prime numbers are only divisible by themselves and 1. Now, what about the even and odd numbers and the irrational or kind of endless numbers that we also have in our standard number system, the non-probability numbers system that everybody still uses? So, standard numbers are permanently split, we could say, into even and odd numbers, right? And they alternate evenly, right? So we have, well, we won't count 0 here because that's an infinite, but we have 1, so I count uneven, 2 even, 3 uneven, and they just keep going on like that. And we see again a bit of a mystery, right? Even, it's always even, uneven, always even. So we know this can't be random. We know it's non-random. We know there is meaning somewhere in that, revealing something, right? But what does it reveal? I would again say, take a minute here, pause the video, see if you can figure it out yourself. Try to look from the perspective of the law of exception, and then I will tell you. So how do we do this analysis? Well, we see that it alternates perfectly and evenly, like it doesn't have any preference, seems like. Perfectly half, but on the other hand, we know that everything must be temporary, right? So how to unravel that clue? Well, what if we look at it from a perspective of time? 1, clearly uneven. 2, clearly even. But together, if I have one even, one uneven, it's kind of balanced, right? Then we move on to the next number, it's uneven again. So now I have kind of more uneven numbers than even numbers. But the next step, it balances out again. So it always goes even, uneven, even, uneven. So we can summarize this structure perhaps as after an even number, it always must become an uneven number. And after an uneven number, it always must become an even number. Now, what's going on with this structure that cannot be? What's going on with this structure that breaks the law of exception again? What's missing? Everything must be temporary. But this structure, after even, it must always become uneven. After uneven, it must always become even. This structure is stuck in time. It's actually an infinite loop. It's changing, seemingly, but it's actually not really changing. It's completely, perfectly predictable. It has no choice. So how do we solve this then? How do we give numbers a choice? Because in the real world, we just discussed it, when we measure things, one very important part of every measurement is that a measurement is always a choice. If 3 people measure a circle, we just mentioned it, and we want them to be very precise, so we say, you know, I want you to measure this circle, but I want you to do like 6 numbers behind the dot, right? Well, each of those persons will give you a very different number. So in reality, every value we measure must always be a choice. So what happens then if we make every number a choice, reflecting reality perfectly? Well, that is what the infinity symbol means in the probability math. It means here you will have to make a choice, because there's no way to know, there exists no real values. So in the end, it's always your choice, my choice, that decides what the value will be. And what happens when we integrate that idea into all numbers with the probability numbers, that's literally how I design it, as I told you in the last video, then the even and odd structure mysteriously completely disappears. It vanishes from the number series. And now we know why we had even and odd numbers, because it cannot be any other way. Because if numbers don't have a choice, well, they can't all be even, they can't all be uneven, so the only way for the universe to solve that problem is, well, I'll just alternate between the two. So again, it was giving us a clue. It was saying, hey, if you ask me this in this way, if you use this tool, then I have no choice but to do this strange alternation because of the choice you already made, right? So in probability numbers, any value only becomes even or odd when you choose it. When you collapse the number, it can become either even or odd. It's your choice. And so the reason that we even have even and odd numbers is because we kind of forgot to include choice in math. There is no choice function in math at all. And because all of reality is about choice, because every value we see, everything we ever write down, it's always a choice. It's not, there are no values that just come. We choose them. And that's why standard math without probability numbers, cannot describe reality accurately, because math makes this strange presumption that numbers, results, just come out of somewhere. You know, we do a measurement with whatever measuring stick, no matter how advanced or complex your measuring stick is, when you get the result, that's a choice. It was either a choice of how you made the system that's measuring it, so that decided what the answer will be, or you're looking at something and you can't be quite sure, so you have to choose. When you use an actual measuring stick, it's like what's close to 3, a little bit closer to 3 than 2. Well, I'll call it like 2.7, right? It's a choice. And so there you have it. 3 times non-randomness in a row, communicating to us perfectly how something's behavior, how it behaves, how it reveals itself, how it's shaped, actually reveals to us, shows us what causes that behavior. It's kind of a true form of magic. Our world is non-random, because this goes for everything you see. Everything we see has a reason. Every single thing that is created by a choice somewhere. And so every little choice that we make matters, because there is no zero. There is no way for any choice to have zero impact. It always has some small but some real impact. And it kind of hopefully makes you wonder why and how you got to see this video, right? Because it matters. It matters to you, it matters to me that you've seen it, it matters who you share it with, it matters that you like and put a comment below what you thought of it. It matters because everything matters. If there's a purpose, it will find us. If there's hope, it will find us. That is the way, kind of, the law of exception tells us the universe really works. When we ask a question, whether we do it with math or in our minds or however what we do, what we see is not random, never random. There can be little purpose, but there's never no purpose at all. So when we do away with nonchalance, when we take what I've heard from many mathematicians, even physicists, after my first video, basically what they were saying is, yes, Flo, this is interesting, but it doesn't really matter, right? So, no, there's nothing that doesn't really matter. Nonchalance is an illusion. Being nonchalant about anything is an illusion. And so in the next video, we're going to talk about energy. We're going to talk about what I actually talked about in the very first video, where I said the law of exception. What it really is, it's a description of the fundamental structure of energy, because everything around us is energy. And so energy works in a certain way. Energy itself is what is forcing everything to be temporary. And if you thought this video was interesting, if this gave you a little science-gasm, a little aha, like, hey, wow, I'm seeing something really cool and new here, this next video will literally blow your mind. So please like and subscribe, tell all your friends about this, share it far and wide, and I'm very much looking forward to the next video where we're going to dive deeply into the structure of energy itself and what it means for us, for being a consciousness, for being a player made of energy in a world that's made of energy, and actually knowing what the central structure, what the fundamental structure of energy is and what we can do with that. So hope to see you in the next video. Have a great weekend. My name is Florian Roos and this is the Law of Exception. Ciao, ciao.